So what we'll do today is the last part you need for your second assignment, which is trigonometric integration. We'll finish all the categories. So last time, recall what we were doing was trigonometric integrals. And so we're doing the three main categories. The first category is we're going to have four cases. So category one is going to be the integral of sine mx and cos mx dx. And so if we have our first case we went through in this is if m is odd or n is odd, doesn't matter which one first, and say m is even. Then what we're really doing is sine 2k plus 1x is equal to sine 2k x times sine x, which is also equal to sine squared x to the power k times sine x. And this is nothing more than exponent laws, but then people don't see it. You can't see the board. Okay, just wait, let me stop share. I'll retry again. I think I might have paused the share at the same time when I paused the computer last time. You see that now? Yeah, there. Technology. So these are exponent laws. This is the trick we're going to use in both of the first three cases. We can't use this trick in the fourth case for the trigonometric integrals. So what we have is now, if I have that scenario where sine is odd, I'm going to steal off one of the odd ones. And then what I'm actually going to do is then we're going to write sine squared x is equal to 1 minus cos squared x, the Pythagorean identity. So under that, guys, we have the integral of sine 2k plus 1x times cos mx dx. It actually doesn't really matter what the m is, but we're assuming he's even. But if one of them is odd, we immediately steal one of the signs and we turn this guy into get it ready for the Pythagorean identity. So now what I see is I'm going to turn all everything into coses because I want this to be my dw or negative dw in this case. So what I'm going to let happen is, how do I get rid of all the coses though? I have to use the Pythagorean identity. This will be the integral of 1 minus cos squared x to the power k times cos mx times sine x dx. Once I've done that, I've set everything up to now correctly use, I'm going to let w equal cos x so that negative dw equals sine x dx. And then I have exactly substitution. This will equal the integral 1 minus w squared to the power k, w to the m times negative dw. Then we're off to the races. We just use FOIL and then we're done. But this is the way to get the substitution to get to the power rule, essentially. I'll do some examples in a second. Category 2 is going to be the same thing, except now if n is even, and m is odd. Now it's just the other scenario. Then what we're going to do is we're going to have that cos 2l plus 1x is equal to cos 2lx plus or times cos x. And then I'm going to use the Pythagorean identity. This is cos squared x to the power l times cos x. And that, of course, is equal to 1 minus sine squared x to the power l times cos x. This is how I use the exponent laws and the Pythagorean identity to get rid of cos this time. And now you can see it, the integral of sine nx times cos 2l plus 1x dx is going to become equal to the integral of 1 minus sine squared x to the power l times sine, actually I can write them together this time. This is sine nx 1 minus sine squared power l times cos x dx. This is now going to be my differential that I want. So I'm going to let w equal sine x this time, and dw will equal cos x dx. Then I have my substitution. I can write this as the integral of w to the n 1 minus w squared to the l times dw. And then I just use the power rule to get rid of this as well. In the third case, if they're both odd, so n is 2k plus 1 and m is 2l plus 1. Then you can choose whichever one you want. You can write it either way for this thing. If they're both odd, you can pick whichever differential you want and you can substitute these out. For case 4, we want to be careful. I'll go through all 4 cases and then I'll do a couple examples of each scenario. So what we have here is both even. If they're both even, if m is 2k and n is 2l, they're both even. And we have to use sine squared x is equal to 1/2 1 minus cos 2x, and cos squared x is equal to 1/2 1 plus cos 2x. Is the identities we have to use. And so the integral of sine 2kx cos 2lx dx is going to become equal to the integral of sine squared x to the power k times cos squared x to the power l dx. And then you're going to have to FOIL all those out. This is going to become the integral of 1/2 1 minus cos 2x to the power k times 1/2 1 plus cos 2x to the power l dx. And then the problem with this is you have to FOIL everything out, and if you get cos squared of 2x, then you have to do the formula again and double the angle until you get to just cos kx's. And then the integral we want to use is we're going to get down to the integral of cos kx, essentially dx which is baby substitution again. The integral of cos kx dx is equal to 1 over k sine kx plus c. That's where you're trying to get to, is get everything to a cos kx from these formulas. So example 1, I'll do an odd case or odd even. So you're given product of sine and cosine. This is a nice one that I like because it's going to be the substitution sine. You can see it almost. Cos is odd, so I'm going to steal one immediately. This is equal to the integral of sine 4x times cos 4x times cos x dx. I steal one of the coses, and then I can see immediately what my differential is. I stole one of the coses to create a differential. Is really what you want to focus on. How do I create a differential? In the sine cosine one, their derivatives turn into each other. For tan and secant, it's going to be different. There's going to be different identities and the derivatives are different. So in this one now, what am I going to do? If I suspect I'm going to let w equal sine x, so that dw is cos x dx, which is exactly what I have, then I need to get rid of all the other coses. These ones have to go away. So I'm going to write this as equals the integral of sine 4x times, I'll go slow, cos squared x squared times cos x dx. Cos squared, I'm going to use the Pythagorean identity to get rid of it now. This is equal to sine 4x 1 minus sine squared x squared times cos x dx. Now I can use my substitution because everything's ready. This is equal to the integral of w to the 4 1 minus w squared squared times dw. That was my substitution. Now I have to FOIL everything out. So this is equal to the integral of w to 4 1 minus 2w squared plus w to 4 dw, which is now just the power rule, the integral. So this is the thing that I didn't show in there. You have to use the binomial theorem and expand those powers if you have them and distribute everything. So this should be w to the 4 minus 2w6 plus w to the 8 dw. Now it's just the power rule. So I apply this immediately. 1/5 w to the 5 minus 2 over 7 w to the 7 plus 1 over 9 w to the 9 plus a constant of integration. What was w? W in this case was sine x. W is sine. So this is how we integrate. And it doesn't matter whether it was, which one was even or odd. What you're asking yourself is you're praying that one of them isn't, they're not both even. You want one at least to be odd. You steal one of the odd piece for the differential. Now that you've stole that one exponent that was odd for the differential, I have an even power left. I can therefore use the squared and use the Pythagorean identity to get rid of the rest of them and then make a complete substitution. Example 2. Let's do okay, yeah, maybe I should do that. Sometimes I'll also throw in where the exponent isn't, one of the exponents isn't rational. Just to throw you off. But the trick is going to be the same. I see that the sign is odd, so I'm going to steal one of those this time. So what do I see? I'm going to write sine 5x as sine 4x times sine x, first of all. And then I'm going to write this as sine squared x squared times sine x, which is equal to 1 minus cos squared x squared times sine x. So what are we going to get? Roughly the same thing. And so this says our integral of sine 5x times cos to the 1/2 x dx, the square root is 1/2 exponent, is equal to the integral of 1 minus cos squared x squared times cos to the 1/2 x times sine x dx. Now what we're going to do is I'm going to use my substitution. I've got the differential I want. So w is going to equal cos x. And so dw is going to equal, or negative dw will be equal sine x dx. Making that substitution, I get the integral of 1 minus w squared squared, w to the 1/2 times negative dw. And now I'm off to the races. All I'm doing is foiling everything out and getting myself the power rule over and over again. So this should be the integral of, when I clean this up, it should be the same thing, negative 1 minus w 2w squared plus w to the 4, and then w to the 1/2 on the outside, which would equal the integral of w to the 9 over 2 minus 2w to the 5 over 2 plus w to the 1/2. Did I do that right? Seems like I have a negative somewhere, error. This should be negative, positive, negative. I didn't put the negative through. I forgot my negative on the outside, it looks like. It should be negative, positive, negative, W. Good. Yeah, I had a typo in mine. Up to the negative, it doesn't matter. So now what do I get? Negative. So we have, this is just going to be negative 2 over 11, w to the 11 over 2, plus 4 over 7, w to the 7 over 2, minus 2 over 3, w to the 3 over 2 plus c. And then w was cos this time. Plus 4 over 7 cos to the 7 over 2x plus 2 over 3 cos 3 over 2x plus c. So they can change the exponent to be weird. The idea is you want to see when you have products of sine and cosine, even if the exponent isn't an integer, they gave as a fractional or square root, they're trying to scare you. When you see an odd one, you want to steal that guy to be the exponent. The other guy is the substitution. So that I see that sine is odd, 5. I know my substitution is going to be cos, and I'm going to get rid of all the other coses. And then that will be the substitution to get back at that. Yeah, that's a useful one. Two different ways. That one. Both odd. Yeah, let's do that one. Okay. I want to do one of the ones that's danger. That's if both powers are even. That's the danger case. These get out of hand real fast, so I'll do basically the hardest one. I'll do one of each. Sine squared x and cos squared x dx. In this case, I get a difference of squares, but that's fine. So what am I doing? In this one, they're both even. So I have to use the identities. This is the integral of 1/2 1 minus cos 2x times 1/2 1 plus cos 2x dx. Now I'm just trying to deal with the trigonometry and FOIL everything out. You have to, if you had powers, if we had magical powers up here, M and L or something like this, then we would have to FOIL everything out first and then multiply them together. I gave myself the first power so I didn't have to do that. But now what are we going to have to do? Multiply this together. So that gives me 1/4 the integral of, it's a difference of squares. So 1 minus cos squared 2x dx. So what am I going to do with that? I have to run the identity on this guy again. This one is cos squared 2x is just equal to 1/2 1 plus cos 4x. Every time we double the angle, we're going to double the angle. It didn't matter whether it was a 2x, I'm just going to double it to 4x. If it's a 4x, I double it to 8x, and then 16 and 32, and you're going to get big powers when we have to FOIL this out more and more and more. So that turns into, again, I use the rule. This is 1/4 the integral of 1 minus 1/2 1 plus cos 4x dx. And then because we get the minus, these ones minus, and I'm going to get 1/4 the integral of 1/2 minus 1/2 cos 4x dx, which I can write, if I really want, is 1/8 the integral of 1 minus cos 4x dx. I just pulled the 1/2 out. What is that going to give me? Now I can compute the cos 4x is now down to cos kx, and I can use the integral of cos kx is 1/k sine kx, and then the integral of 1 is obviously x. So this becomes 1/8 x minus 1/4 sine 4x plus c, which is, if you really want, x/8 minus 1/32 sine 4x plus c. This is the idea. We cannot any longer, when they're both even, we can't use the Pythagorean identity. We have to use the fact that sine squared x is 1/2 1 minus cos 2x, and cos squared x is 1/2 1 plus cos 2x. These are the identities I have to use specifically. Great. Yeah. So category 2 is integrating the integral of tan nx and secant mx dx. And there's going to be certain cases, but what you're going to want to do is you want to focus on the fact that what are our differentials this time? If you're going to make we want to make a substitution is the idea. Hopefully you can see from the first cases, we make some kind of substitution in the odd cases. So we want to do the same thing here, if possible. So what are my differentials? If I let W equal tan x, let's look at the possibilities, or we're going to let W equal secant x in this case. So look at what the differentials are. This is what I need to find and steal from the problem that you're not seeing. Here's a kitty. What are you doing, kitty? Being bad. This says that if I let W equal my tan is my substitution W, then I'm going to get dW is secant squared x dx. And so what I'm going to want to do is when I do that, I'm going to want to steal two secants from something and then get rid of all other secants. So we want secant to be even in this case. We want it to be even because then I can get rid of, because then secant 2lx equals secant 2l minus 2x times secant squared x. I'm going to steal two of them. That's it. I just added 2 and subtracted 2 in my exponent. So 2l minus 2 plus 2, and then I stole 2 of them. And then I can write this as secant squared x to the l minus 1 times secant squared x. And then I can write this as, what is secant? 1 plus tan. That's what's going to happen to secant if I do that. If I want W, my substitution, it's better to think of them as substitutions that I need versus these cases. If I want W to be secant x, then I'm going to have dW is secant x tan x dx. And then if I have tan, I want that to be odd this time, because if I have 2k plus 1 x, this will be tan 2kx times tan x. And then I can write this as tan squared x to the power k times tan x. And then this is secant squared x minus 1 to the power k times tan x. I'll use this in a second to show you. Kitties, enough. Yeah. Just a second. It's not coming up there. The young one's bothering the older one, and so that's why she hisses like that. Okay, I'm easily distracted too. So those are the cases, those are the real differentials we're looking for. And so there's going to be there's going to be 4 cases again about the exponents, but I wouldn't view it that way. In the first case, if what you're looking for is you want secant to be even is the first thing you're looking for, or tan to be odd. If that's the case, then you're good to go, because then we have these 2 substitutions. If they're both, then okay. If they're neither, then we have to use something, and we have to be careful and get our way out an entirely different way. So what are the cases now? If secant is, I don't care about the tan, I just want the secant power to be even. So that's m equals 2l. Then what we're going to get is the integral of tan nx secant 2lx dx. Everything will happen just the way that I said. The integral of tan nx stays, we don't alter it, because that's going to be our substitution. I do secant squared x to the power l minus 1 times secant squared x dx. And now I have my differential. I'm going to let w equal tan x. Then dw is going to equal secant squared x dx. Then I can make my substitution. Well, first of all, this becomes the integral of tan nx times secant is 1 plus tan x squared x to the l minus 1 times secant squared x dx. Now I make my substitution. This is the integral of w to the n, 1 plus w squared to the l minus 1 times dw. And then we're off to the races. So the things you're looking for is secant even, tan odd. Those are the good ones. If they're both, then you can choose whichever one you want. And if they're neither, that's the dangerous case in this case, in the tan scenario. So case 2. you want tan odd. If that happens, then what we're going to get is we're going to get the integral of tan 2k plus 1x. The reason we need tan odd is because when I steal one, I have to steal one from both this time. Secant mx dx. So first of all, what I'm going to do is write this as the integral of tan 2kx secant m minus 1x, and then times secant x tan x dx. I stole a power from both of them, from secant and from tan. But when I steal from tan, what's left has to be even. So I had to start out with odd, because now I want to turn, because I can see my differential, secant tan, I know my substitution is going to be secant, so all the other tans have to disappear, and I have to disappear them with the Pythagorean identity. So this becomes the integral of secant squared minus 1 to the k times secant m minus 1x times secant x tan x dx. Now I'm ready for my substitution. My substitution will be w equals secant x. Then dw is going to be secant x tan x dx. And we're off to the races. When I make that substitution, I get that this is the integral of w squared minus 1 to the power k, w to the m minus 1 dw. And then I just use FOIL and the power rule to get myself out of this again. Case 3, if we have both of those cases, that's a good case. If n is even and m is odd, or sorry, if n is odd and m is even, if you have both of those, then this is good. Then choose either case 1 or 2. The dangerous case is case 4, when tan is even and secant x power is odd. Danger. So let me see. That's the way I would do these ones. Yeah. So the way I would do this is, first of all, what I'm going to do is we're going to do strategy. Tan is even. So I can turn all into secants. And then I want to use, then we use a reduction of order formula for secants. This is the worst case. I probably won't put it on an exam because it takes quite a while to do. But then we use reduction of order. For secant x. So what do I mean by that? I'm going to have the integral of tan 2kx plus secant is odd, specifically 2l plus 1. This is the bad case. You want secant to be even, I have odd, or I want tan to be odd, I have even. This is bad. But what I can do is write this as the integral of tan squared x to the power k secant 2L plus 1x dx. Then I can get rid of all the tans, is what it's saying. I can write this as secant squared x minus 1 to the power k times secant mx dx. Now it's all secants. Then I use reduction of order. Let me do one of the reduction of orders. I just want to see which one I did in my notes. Okay, let's do reduction of order. So let's do that for secant. What they mean by reduction of order is they're trying to reduce the power of the integral. So say I have the integral of secant nx or mx dx. What we're going to use is integration by parts. So I'm going to write this as the integral of secant m minus 2x times secant squared x dx. And then I think to myself, who can I make to be dv, and who can I make to be u? You want to make u the thing that you can differentiate, which I can very well. And then I want to make dv the thing I can integrate. So u is going to be secant m minus 2x, then du is going to be m minus 2 times secant m minus 3, but then by the chain rule times the inside, which will be secant times tan. So this is not a mistake. You can work it out, but that's the different dx. And then dv is going to be secant squared x dx. So v is going to be tan x. There's my integration by parts. So what does that give me? So my integral, let's call this I am. The integral, the order power of m is now equal to, by integration by parts, secant m minus 2x times tan x, u times v, minus the integral of v du, tan x times du, which is m minus 2 secant m minus 2x tan x dx. I'll clean that up. So that equals secant m minus 2x tan x minus, now I have an m minus 2 there, the integral of secant m minus 2x times tan squared x dx. Well, that's good because tan squared I can turn back into secant. So that's going to equal the secant m minus 2x tan x minus m minus 2. And now what do I have? The integral of secant m minus 2x times secant squared x minus 1 dx. I turn the tan back into secant. Then I distribute that through. This is secant m minus 2x times tan x minus m minus 2, the integral of I again. I am, and then now plus m minus 2, the integral of secant m minus 2x dx. And there's the reduction of order. Now I have to solve for the appropriate one. what that tells me is, what do I get? I get im plus m minus 2im equals secant m minus 2x tan x plus m minus 2 the integral of secant m minus 2x dx. So if you add that one up, I get m minus 1 im equals this thing, or blah, 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 blah. What I get is finally im is equal to 1 over m minus 1 secant m minus 2x tan x plus m minus 2 over m minus 1 the integral of secant m minus 2x dx. They call it reduction of order now because I've reduced the order of the m to an m minus 2. So what that says essentially is, if you know a power of secant, it doesn't matter what it is, you keep using this reduction power. If I know secant 5, then I can reduce this and use this formula to get an integral of secant cubed. Secant cubed is integration by parts. Again, they may have shown you this in any of the literature they show you. I guess I'll show you right now. Then I get to secant 1 is a dirty trick. If I have even powers, then this is even better because I know the integral of secant. So this formula is reducing you to, regardless of what the case is, if I have this bad case of tan powers or even, secant powers are odd, what I do is I use the fact that the tan powers are even, turn everything into secants. Now I just have an integral of powers of secants. Then I use this horrible reduction formula to integrate each of the powers of secants, getting down to, you want to know the low level ones for secant. I only have a few minutes left. The last thing. So that's the outlier case. I'll do more of these at the beginning next time. I was looking at your assignment. Is the only one that I have to worry about is he gives you this integral on the assignment. I didn't get to pick all the questions. The integral of sine theta cos theta, and then cos 3 theta, something like this. So I'll start you off with that, but here's the formula, here's the idea that they want. The cotan cosecant 1 is the same as the tan cotan 1. Like, the only difference is there's a negative. But first of all, the first hint is sine theta cos theta is equal to 2 over 2 sine theta cos theta, which is 1/2 to sine theta cos theta. You see, now that's a trig identity. That's 1/2 sine 2 theta. So that integral becomes the integral of 1/2 sine 2 theta cos 3 theta d theta. And that's where I want to start off with this last case, where sometimes you can have product of sine and cosines. If you have those, what are we going to do? So if I have, yeah, that's the one I want. We know that sine A plus B is equal to sine A cos B plus sine B cos A. And I also know that sine A minus B is equal to sine A cos B minus sine B cos A. Now, if I add those things together, these will cancel off. And we're getting, so what we're getting at is, do you see what the clever trick is going to get here? Now on this side, we get sine A plus B plus sine A minus B is equal to 2 sine A cos B. Or the thing we want, if you have a sine AX or a sine A times a cos B, this is equal to 1/2 sine A plus B plus sine A minus B. That's what you want to use right here. You have A is equal to 2 theta and B is equal to 3 theta. So this is how you integrate these things. First of all, he put 3 trigonometric ones in there to trick you. You can combine those two with an identity to make that sine 2 theta. Once I do that, I want to use this last identity in the sum and difference formulas to add these appropriately to get the formulas for when I have products of 2 sines or 2 coses or a sine and a cosine. This is how I get myself out of these things. So I think that should do you for assignment. I'll continue with the trigonometric integrals and do a few more examples, and then we'll do trigonometric substitution next week. I think that should be good. I have to give a midterm later on today in about an hour. So have a good weekend. Your assignment's also due on, even if it says in the course outline 11, I put it's due at midnight on Sunday, so you can have the extra day, because that's what you'd want to do on a Saturday night, is do a bunch of, yeah, that's what I'm saying. A and B, everyone, this is the whole point of a formula every time. A and B are just arbitrary. You can replace them with everything. This is the point of a formula. Replace A with 2 theta and 3 theta. This is what they are. Yeah. Again, yeah, make A 2 theta and B 3 theta. The formula works regardless of what A and B are. Yeah. It doesn't matter. You can put the variable or sine x in there. Yeah, sine AX and cos BX if you want. If you want to put the variables in there, it doesn't matter. The formula still works. So that should do everything that you need. I think everything else on there should be things that you covered. I was looking.